Please turn to page 9 in your Unit 1 notes packet. We're going to examine how to solve quadratic equations by factoring. Let's begin with some vocabulary. A monomial is an expression that is either a number, a variable, or the product of a number and one or more variables. There's one term, that's why it begins with mon. A binomial such as x plus 4 is the sum of two monomials. Bi means two, so there's two terms separated by a plus or minus sign. A trinomial such as x squared plus 11x plus 28 is the sum of three monomials, because tri means three. When the process of multiplying polynomials is reversed, we call this factoring. And polynomial simply means there could be many terms. So mon means one, so there's one term in a monomial. Bi means two, there's two terms in a binomial. Tri means three, so there's three terms in a trinomial. And poly means many, so when we say polynomials, it covers the whole spectrum. But so today we're going to be focused on factoring. So this idea that when we take a standard form equation and factor it, or break it down into its two factors that we would multiply to get the standard form, it's called factoring. So we're reversing the process of multiplication. A polynomial in factored form will look like this. X plus 3 and x plus 1 are factors. We could multiply them together to get our product, which is x squared plus 4x plus 3. So this is an example of a polynomial in factored form. This is an example of a polynomial in standard form. Reminder that factors are two or more numbers or algebraic expressions that are multiplied to produce a specific product. We are going to use the process of reverse FOIL in order to factor these polynomials. Diamond in a box is another good strategy that if you remember how to use that, you could use that instead. When we reverse FOIL, we set up our sets of parentheses. We know that this trinomial, since it has three different terms, will factor into the product of two binomials. So we'll have two terms in each of these parentheses. To figure out what we need, we have to think in reverse. So our first term is x squared, and I know that that comes from multiplying the first term in each binomial. So I'm thinking to myself, what would multiply to x squared? And the answer is x times x. So my first term in both binomials must be x. Then I focus on the 20. I have to find two numbers that are going to multiply to 20 to place here as my last terms, since this is the product of the last terms. However, I also have to consider the middle term. Whatever I place here and here will be multiplied by the x's and has to add to come up with negative 9x. So when I consider the factors of 20, I know I have 1 and 20, 2 and 10, or 4 and 5. The only two that would add to give me 9 would be 4 and 5. So I'm going to fill in 4 and 5. And because this is a positive, but this is a negative, I know that the signs must both be negative. So that it'll multiply to positive 20, but add to negative 9. And we do a quick check to make sure we have the correct factorization. So we take x minus 4 and multiply it by the x minus 5. We get x squared minus 4x minus 5x positive 20. So altogether x squared minus 9x plus 20. It checks with the original, so we know we have the correct factorization. On to letter B. So again, because there's 3 terms, I have a trinomial, so I know it'll factor into the product of 2 binomials. I know that my first terms have to multiply to give me this first term. So I'm thinking, what times what gives me x squared? The answer is x times x. Then I consider my last term, and I think about what I could place here and here that will multiply to negative 12, but it has to also add to positive 3. So when I consider the factors of 12, we have 1 and 12, 2 and 6, 4 and 3. If I need to get 3, I can try all of these. So I can try a positive 1 and a negative 12. That give me negative 11. And the reason I'm doing opposite signs is I need to get negative 12 when I multiply, so one would have to be positive and one would have to be negative. I could also flip it and do negative 1 and positive 12. So that's going to give me positive 11. I could do 2 and negative 6, but that's negative 4. I could do negative 2 and positive 6, but that's going to give me 4. I could do 3 and negative 4, but that gives me negative 1. I could do negative 3 and positive 4, but that gives me 1. So I've run through all of my possible factors that would multiply to negative 12, but none of them add up to the required 3. So what this leads me to conclude is that this cannot be factored. So factoring is a great strategy to use with quadratics. Unfortunately, it doesn't always work. So sometimes we run into this where things cannot be factored. On to letter C. So again, I start with a trinomial. It's got 3 terms, so I know it's going to factor into the product of 2 binomials. I consider my first term of x squared. And I think to myself, what can I place here and here to get a product of x squared? The answer is x and x. Then I look at the negative 18, and I think, what would multiply to negative 18, but add to negative 3? And so what I come up with is negative 6 and positive 3. And I should do a quick check. So if I take x plus 3 times x minus 6, I get x squared, 3x, negative 6x, and negative 18. So altogether, x squared minus 3x minus 18, and it checks with the original problem. Okay, so we're on to our key concept box. There are some special factoring patterns that we can learn as well, and the biggest one is difference of 2 squares. So when we have a binomial that is subtraction, so there's the difference, and we have 2 perfect squares. We follow this pattern known as the difference of 2 squares. And the factorization will be the same binomial, only one will have a plus sign, the other will have a minus sign, so that when we multiply, we get a negative for this final term, but the outsides and the insides will cancel each other out. What we place into those binomials are the square roots of each term. So for example, if we have x squared, take away 4. If I square root x squared, I get x, so that's the first term in each binomial. If I square root 4, I get 2, so that's the second term in each binomial. I need one with a plus, one with a minus. So that if I multiply this out, my outsides and my insides are going to cancel, leaving me with only 2 terms. So if we do x minus 2 times x plus 2, we get x squared, negative 2x, positive 2x, and negative 4. So So we get x squared plus 2x minus 2x minus 4, which is x squared minus 4 when we simplify. Another pattern that you could learn is the perfect square trinomial. So when we have something that appears in this form, it will factor into the same binomial twice, so we condense and write it as that binomial squared. So here are some examples of that. X squared plus 6x plus 9 would factor into x plus 3 times x plus 3. So rather than writing it twice, we just write it as x plus 3 quantity squared. X squared minus 4x plus 4 factors into x minus 2 times x minus 2. So rather than writing it twice, we write it as x minus 2 quantity squared. Difference of squares you absolutely have to know. Perfect square trinomial is something that you just kind of notice and condense it when you're finished factoring. Okay, let's look at some examples of special factoring patterns. In 2a, we give you the binomial x squared minus 49. Another way you could think of this is as x squared plus 0x's take away 49. So what I noticed is that we've got one perfect square here, another perfect square here, and they're separated by minus, so it's the difference of two squares. And so it factors into x plus 7 times x minus 7. Because I need the first terms to multiply to the x squared, I need the last terms to multiply to negative 49, but I need the center to add to 0. So negative 7x plus positive 7x gives me 0x. Then we can verify that we are correct by multiplying this out. And you should always do this. You should always do a check to ensure that you do in fact have the correct factorization. So if we take x minus 7 times x plus 7, we get x squared, negative 7x, positive 7x, and negative 49. So when you add that up, x squared plus 7x minus 7x minus 49, the center adds to 0x. So we're left with our original binomial x squared minus 49. We've checked. This is the correct factorization. In 2b, they give us d squared plus 12d plus 36. So I need to factor this trinomial into the product of two binomials. I know that my first terms have to multiply to equal d squared, so that would be d times d. My last terms have to multiply to 36, but I also need to make sure that I can add up to 12d. So that would be plus 6 and plus 6. Let's check to ensure we have the correct factorization by multiplying it out. So we'll take d plus 6 times d plus 6. D times d gives us d squared. D times 6 is 6d. D times 6 is 6d. 6 times 6 is 36. So if we write it out, we have d squared plus 6d plus 6d plus 36, or d squared plus 12d plus 36, which checks with the original. Now instead of writing d plus 6 twice, we condense and write it as d plus 6 quantity squared. At this point, move on to part C and D, and then come back and finish your notes. Remember, when you're trying parts C and D, if you have two perfect squares separated by subtraction, you'll use difference of squares. And if you factor and get the same quantity twice, we condense and write it as that quantity squared. good luck with the remaining 2 examples, and come on back. When we solve quadratic equations, we call the solutions to the equations roots of the equation. Other names for the solutions are zeros and x-intercepts. If the quadratic can be factored, we can then use the zero product property to solve it. So the zero product property states, if the product of 2 expressions is 0, then one or both of the expressions equals 0. So in terms of algebra, if a and b are expressions and a times b equals 0, then either a has to equal 0 or b equals 0. There aren't any 2 numbers that aren't 0 that have a product of 0. In order to multiply and get 0 as your answer, you must have 0 times something else. We've been using this when we've worked with intercept form, and we find the 2 x-intercepts in order to average them to find the vertex. To find those x-intercepts, we've been applying the zero product property. Here's another example. If you have the binomial x plus 5 times x plus 2 equals 0, then either the first factor x plus 5 must equal 0, or the second factor x plus 2 must equal 0. So when we solve this first one, if we take away 5 from both sides, we see x would have to equal negative 5. And when we solve the second one, x plus 2 equals 0, take away 2 from both sides, x would have to equal negative 2. Let's take a look at a couple examples. Okay, so the first example, they give us x squared minus 5x minus 36 equals 0, and they ask us to determine the roots of the equation. Remember that roots is another way of saying the zeros or the x-intercepts. So our first step is to factor it. So I have a trinomial that I know should factor into the product of 2 binomials. So I set up my parentheses and think about how to multiply to get my first term. And I would need x times x, so I put that in as my first term. Then I consider the last term. I need to multiply to negative 36, but I have to add to negative 5. So that means that I would need 2 numbers whose product is negative 36, but whose sum is negative 5, and the 2 numbers I come up with are negative 9 and positive 4. Because negative 9 times positive 4 gives me negative 36, but negative 9 plus 4 gives me negative 5. So now I set each factor equal to 0 using the zero product property, and I will solve them. So I'll add 9 to both sides for the first one to determine that x could equal 9. I'll subtract 4 from both sides for the second one to determine that x could equal negative 4. And those are the 2 roots of my quadratic function. So the correct response for that multiple choice example would be letter C. In example 4, they ask us to solve the equation x squared minus x minus 42 equals 0. So again, my first step is to factor. I'm starting with a trinomial that I know will factor into a binomial, so I set up my 2 sets of parentheses, and I think about how to multiply to get the first term of x squared. So I'm going to need x times x. Then I think about how to multiply to get negative 42, but add to get negative x. So the 2 numbers I come up with are negative 7 and positive 6. I check myself. X times x gives me x squared. The outside terms gives me positive 6x. The inside terms gives me negative 7x. So negative 7x plus 6x gives me negative x. Negative 7 times positive 6 gives me negative 42. So I have the correct factorization. I'm ready to use the zero product property and say, okay, so either the first factor equals 0 or the second factor equals 0. I solve both of these using inverse operations to determine that x could equal 7 or x could equal -6. And those are the two solutions to that original equation. Let's take a look at an application of factoring and zero product property. So the nature preserve. A town has a nature preserve with a rectangular field that measures 600, as you can see they've labeled it here, meters by 400 meters. The town wants to double the area of the field by adding land as shown. So they're going to add the same amount to the length, x units, as to the width, x units here as well. Find the new dimensions of the field. So first of all, we know that we're starting with 600 meters for the length, and we're adding on some amount we need to solve for. In order to find the total area of the land, since that's the measurement they're bringing up, we need to multiply this length, 600 plus x, by the width, which would be 400 plus x. So I'll multiply that by the width plus this x amount that we're going to determine. And they want that to equal twice the area of the current field. So the area of the current field would be 600 times 400, but they want it to be double that, so I need to multiply by 2. So I need to multiply out both sides of this equation so that I can get it into the correct form. In order to solve, it's got to be equal to 0, and right now it's not. This does not equal 0, so I'm going to have to multiply everything out, combine like terms, and get it to equal 0. So on the left-hand side, when I take my first term, 600 times 400, I get 24 for the 6 times 4, and then I need the 4 zeros. So in other words, 240,000. Then I have my outsides, which would be 600x, my insides, which would be 400x. Plus my last term, x times x, will give me x squared. And then this equals the product of the right-hand side. Well, we already did 600 times 400. We know it's 240,000, but then we have to double it. So we have 480,000. And now I need to combine like terms and get everything on one side and set equal to 0. So I'm going to put my x squared first, combine my x's. 600 and 400 gives me 1000x. And then 240,000 take away 480,000 will leave me with negative 240,000. So what I did there was I put this term first, x squared. I combined these x's to get 1000x. Then I subtracted this value from this side, and for balance I had to subtract it from the constant over here as well. So 240,000 minus 480,000 gives me negative 240,000. So that now it's equal to 0. I can factor and use the zero product property. So I'm going to set up my binomials. And these are large numbers, but we can do it. My first terms have to multiply to give me x squared. So it's got to be x times x. Then I have to multiply to get negative 240,000, but add to get 1000x. So if I focus on the 24 and the 10, I can figure out that factors of 24 that are going to add to 10 would be 12 and 2. And then I just need the zeros, since we're dealing with such big numbers. So if I do 1,200 and negative 200, this will work because I'll get positive 1,200 minus 200 will leave me with 1,000. And 1,200 times negative 200, well, 12 times negative 2 is negative 24. And I have 1, 2, 3, 4 zeros. So it would equal negative 240,000. Now I'm ready for zero product property, so I set each one equal to 0. And I'll solve to determine the value of x. So here I need to subtract 1,200 from both sides. And I get x equals negative 1,200. But I can throw that out right away because it's impossible for x to be a negative number because they want to add on additional land. They're not making it smaller, they're making it larger. So I can't have a negative amount of land for this scenario. So I'm depending upon my second solution. And for this one, I get x equals 200 meters. So what I'm saying is that they must have added 200 meters to each dimension of the field to double its area. And I can check myself. So the new length would be 600 plus 200, or 800 meters. The new width would be 400 plus 200, or 600 meters. And I need the total area to be 480,000 because that's twice the original area of 240,000. So if we find the area and we take 800 times 600, we do in fact get 480,000. So it checks. They need to add 200 meters to both the length and the width in order to double the area of the original field. Another useful application of factoring is to rewrite equations that are in standard form in intercept form. So let's take a look at the first example. They give us y equals x squared minus x minus 12. So if I want to factor this trinomial, I set up my two sets of parentheses for my two binomials. I know the first terms have to multiply to x squared. So it's going to be x times x. My last terms have to multiply to negative 12, but they also have to add to negative 1. So I put in negative 4 and positive 3. I know that I need the larger value to be negative so that it'll add to negative 1. It asks for the zeros, so I set it equal to 0, and then I can use zero product property in order to solve. So I know that either x minus 4 equals 0 or x plus 3 equals 0. I use inverse operations to solve, and I determine that x equals 4 is one. The other one occurs at x equals negative 3. So my zeros are 4, 0 and negative 3, 0. Pause the video here. Use this example as a guide to complete example B. Be sure to state your final answer as ordered pairs. They ask you for the zeros. Those are points on the graph, so you need to write them as such. When you're done with example B, come on back to examine what happens when we have a leading coefficient that's not 1. Alright, so let's see what happens when we change the leading coefficient from just being a 1 to being any value. So when we've got an a value that is not equal to 1, how does our factoring process change? Well, it doesn't change too much. We just have to think a little harder and take some additional things into account. So in example 1, we have 5x squared minus 17x plus 6. And so I have a trinomial. I know that's going to factor into the product of two binomials, so I set up my parentheses. I'm still focused on what to put in my first term positions so that I multiply to my first term. Because it's 5x squared, that's prime, so my only options to multiply to 5 are 5 and 1, so I'll do 5x and 1x. I have to multiply to positive 6 for my last terms, but they have to add to negative 17. So that's where this leading coefficient comes in. This is going to be multiplied by whatever I put out here in the farthest position. And whatever I get for that product is going to be added to this inside product, and it has to give me negative 17. I can fill in my signs. I know they both have to be negative because I need to get a positive product but add to a negative. And so now I think about factors of 6. 3 and 2 come to mind, and I notice that if I put the 3 here, 3 times 5 would give me 15, which is close to my goal of 17. So if I put the 3 here, get 15, and I put the 2 here, this would be 2. So I'd have 15x and 2x, which would add to the 17x. So I'm going to strategically place the 3 here and the 2 here, and then I'm going to check to ensure that I have the correct factorization. So I'm going to do 5x take away 2 times x take away 3. I'm going to multiply 5x times x and get 5x squared. I'm going to take negative 2 times x and get negative 2x. I'm going to take negative 3 times 5x and get negative 15x. I'm going to take negative 3 times negative 2, which is 6. So when I write this out, I've got 5x squared minus 2x minus 15x plus 6, which is 5x squared minus 17x plus 6, and it checks. So this is the correct factorization. On the second example, they gave us 3x squared plus 20x take away 7. So again, I set up my binomials. I know that what I put in the first positions has to multiply to the first term. Again, 3 is prime, so I know it has to be 3x times 1x. Remember, when I use the term prime, that means that the number is only divisible by itself and 1. So my only options are itself and 1 for its factors. The same is true for 7. It is prime as well. So my only options are 7 and 1, but I need to think, do I want the 7 here, so it's multiplied by the x? Or do I want the 7 here, so that's multiplied by the 3? Because I need to add to 20x, that's pretty large, so I want the 7 out here, so it can multiply by the 3. So I'm going to go ahead and fill in the 7, and that would put a 1 right here, so that 1 times 7 is 7, but I need it to be negative 7, but add to positive 20. So I want the bigger one to be positive, since the sum comes out positive, and I want the smaller one negative. And so now I have to check myself. So we're going to multiply this out, and remember, you can always use FOIL. I'm just showing it with the box. So we've got 3x minus 1 times x plus 7. 3x times x is 3x squared. X times negative 1 is negative 1x. 7 times 3x is 21x. 7 times negative 1 is negative 7. So we've got 3x squared minus 1x minus 21x minus 7. 3x squared plus 20x minus 7. Checks with the original, so we have the correct factorization. Okay, so example 3, they give us 6x squared plus x, take away 15. Starting with a trinomial, I know it should factor into the product of two binomials, so I set up my parentheses. This time I don't have a prime number here, so I do have some options. I could do 3 and 2 or 5 and 1. I'm going to start with 3 and 2, and if it doesn't work, then I would go back and reconsider 5 and 1. There is some guess and check involved in this. So again, I'm going to start by trying 3x and 2x. I have to multiply to negative 15, so I know I need 1 plus and 1 minus in here, but I'm not sure which one is which, so I'll leave it blank for now. With 15, I've got 15 and 1, or 3 and 5. I'm thinking 3 and 5 since I only need to add to 1, but let's see if I can make it work. So if I put the 3 here, it would multiply by the 3x to get me 9x. Then I'd have the 5 left for here, times the 2 would give me 10x. So I'd have 9x and 10x, and they're going to have a difference of 1, so I think that's a good plan. So I'm going to put the 3 here, and the 5 here. Because it adds to positive 1, I want the bigger one to be positive, so I'm going to put the plus sign with the 5, and the minus sign with the 3. And again, we need to check to make sure we have the correct factorization. So we have 3x plus 5, 2x minus 3, 3x times 2x is 6x squared, 2x times 5 is 10x, negative 3 times 3x is negative 9x, negative 3 times 5 is negative 15. So altogether we've got 6x squared plus 10x minus 9x minus 15, or 6x squared plus x minus 15, which checks with the original. Let's do one more example together, and then we'll have you try some on your own. So number 4, they give us 9x squared minus 64. And I notice right away that it's a binomial, only 2 terms. It's a subtraction, so that's a difference. 9 is 3 squared, so this is 3x quantity squared, and 64 is 8 squared. So this is really 3x quantity squared minus 8 squared, which means it fits one of our special patterns. It's the difference of 2 perfect squares. So I know that it's going to factor into the same binomial, only one with a plus sign and one with a minus sign. And the first term will be the square root of this, or 3x. And my second term is the square root of 64, which is the 8. So it's 3x plus 8 and 3x minus 8. And again, you should always check to make sure you have the correct factorization. So if we do 3x minus 8 times 3x plus 8, 3x times 3x is 9x squared. 3x times negative 8 is negative 24x. 8 times 3x is 24x. 8 times negative 8 is negative 64. So if we write it out, 9x squared minus 24x plus 24x minus 64. And when we combine like terms, we've got 9x squared minus 64. So it checks. Okay, so now I'd like you to pause the video and try examples 5 and 6. Then come back to the video so I can give you a helpful hint on number 7. Example 7 shows us an example where we have to do 2 steps of factoring. So we've talked about factoring trinomials and binomials that have special properties, but now we need to talk about something called greatest common factor and GCF factoring. So when I take a look at the binomial given to us in 7, we've got 5x squared minus 45. I notice that 5 and 45 both end in 5, telling me they're both divisible by 5. So my first step is to factor out their GCF, or greatest common factor, which is 5. So I'm going to factor out the 5, and I think to myself, 5 times what would get me 5x squared? The answer is x squared. Then I think about 5 times what will give me 45? The answer is no. So I've achieved the first stage of factoring. I have properly factored out my greatest common factor of 5. To check myself, 5 times x squared will give me 5x squared. 5 times negative 9 will give me negative 45. Now I'm ready to factor this binomial. I notice it's subtraction, so that's a difference. This is a perfect square, and 9 is 3 squared. So I'm going to use my difference of squares pattern. I have my GCF of 5 that just comes along for the ride. I set up my two binomials. I need x times x to get x squared, and I need a positive 3 and a negative 3 so that it will multiply to negative 9, but negative 3x plus 3x would give me 0x in the middle. So now to check that I have the correct factorization, I'll first multiply out the binomials. And so we have x plus 3 times x minus 3. And we get x squared, 3x, negative 3x, and negative 9. So we still have the 5, and now I've got x squared plus 3x minus 9, which will simplify to 5 times x squared minus 9. And then if I distribute the 5, I get 5x squared minus 45, which checks with the original binomial. So I have the correct factorization. Let's try another example. So number 8. They give us 6q squared minus 14q plus 8. So I begin by checking all three terms, and I realize they're all even. 8, 14, 6. So I can factor out a 2. So I'm going to factor out a 2. So I'm thinking 2 times what gives me 6q squared. The answer is 3q squared. So then I'm thinking 2 times what gives us 14q. The answer is 7q. And I'm just keeping the signs all the same because I'm factoring out a positive value. So now I'm thinking 2 times what gives me 8. The answer is 4. So I successfully factored out my greatest common factor of 2, and now I need to focus on factoring this trinomial. So the 2 just comes along for the ride, and I set up my two sets of binomials. I have to multiply to 3q squared. Luckily 3 is prime, so my only options are 3 and 1. I also have to multiply to 4, but I want to add to negative 7. So because it's a positive product but a negative sum, that tells me they're both minuses. And I consider, do I want the 4 here? So I'll have negative 4 plus negative 3. Or do I want the 4 here? So I'll have negative 12 and negative 1. Since I want to add to negative 7, I don't want to multiply the 4 by the 3, so I'm going to put it in here with the 3. Put the 1 over here. I could have also tried 2 and 2, but since I saw I had 7, and I've got 3 and 4, I know they add to 7 already. So I set it up so that I could have 3 plus 4 to get 7. So again, let's check to make sure we are correct. So let's multiply out the binomials first. So we have 3q take away 4 times q take away 1. So we get 3q squared minus 4q minus 3q positive 4. So we've got 3q squared minus 4q minus 3q plus 4, but I still have the 2 on the outside that I didn't distribute in. If I combine like terms, I have 3q squared minus 7q plus 4. Then I distribute my 2 to each term. So I have 6q squared minus 14q plus 8, which checks with the original, so I have the correct factorization. Now I'd like for you to try number 9. Pause the video, make sure to factor out a GCF first, then see if you can factor the remaining trinomial into the product of two binomials. Then come back for number 11. Okay, so let's put it all together with number 11. Let's solve this quadratic equation that has an a value of 3 by factoring and using the zero product property. So my first step is to factor. When I look at my three terms, I've got 3, 10, and negative 8. Their greatest common factor is 1, so I don't have to factor out a GCF because it wouldn't change anything. So I set up my two sets of parentheses for my two binomials. Still set equal to 0. I look at my first term, it's 3x squared. 3's prime, so I know it has to be 3x times x. Then I consider my last term of negative 8. So that tells me that if I'm going to multiply to a negative, I need 1 plus 1 minus, but I don't know which one is which yet. And I've got to get a total sum of 10. So with 8, I've got 1 and 8, or 2 and 4. Right away, I'm thinking about how to get a difference of 10, since 1 has to be positive, 1 has to be negative. So I'm thinking maybe 4 and 2, because if I put the 4 here and multiply by 3, I'll get 12. If I put the 2 here, 12 and 2 have a difference of 10. So that's my plan. Because the sum comes out positive, I want the bigger one to be positive. So I'll put a plus here and a minus here. And I'll check myself to see if I have the correct factorization. So I'm going to multiply 3x minus 2 times x plus 4 and get 3x squared minus 2x, 12x, and negative 8, or 3x squared plus 10x minus 8, which does in fact check. So I know I have the factorization right. Now I'm ready for the zero product property. So I set each factor equal to 0, because if I'm going to multiply to 0, one of the factors must be 0. To solve the first one, I add 2 to both sides, and I get 3x equals 2. Then I divide by 3 to determine that x equals 2/3. So there's one solution. For the second one, I subtract 4 and determine that x equals negative 4 is my second solution. And remember, you can check these by taking your x value, substituting it in for the x, following the order of operations, and you should see that you do in fact get 0. Okay, the last example we're going to do in this set of notes is number 12. And we've got a few steps to do before we're even ready to think about starting to solve. Namely, combining like terms and making sure it's set equal to 0, because to solve a quadratic function, it must be set equal to 0. So I'm going to move my 4p over to join the negative 16p, and so we'll have 5p squared minus 20p plus 15 equals negative 5, and then I'll add 5 to move that to the other side. So we have 5p squared minus 20p plus 20 equals 0, and that was my first goal, getting it set equal to 0. Next thing I notice is that I've got 5p squared, negative 20p, and 20, all of which are divisible by 5. So we're going to factor out my greatest common factor of 5. So I'm thinking to myself, 5 times what gives me 5p squared? The answer is p squared. Then 5 times what gives me 20p? The answer is 4p. And then 5 times what gives me 20? The answer is 4. So I factored out my GCF. I can actually divide the GCF away, because on the right-hand side, 0 divided by 5 gives me 0, and on the left-hand side, it just divides out from the 5 that I factored out. So now I can think about factoring this trinomial. So my first terms have to multiply to p squared, so it's p times p. Got to multiply to 4, but add to negative 4, so I want negative 2 into negative 2. Or the quantity p minus 2 squared, So now I can solve. I can square root both sides and get p minus 2 equals 0. I can add 2 to both sides and determine that p equals 2. And if you plug this into the original equation, you'll see that it works out. So if we do 5 times 2 squared minus 16 times 2 plus 15, I'm checking to see, does that equal 4 times 2 minus 5? Well, on the left side, we'll have 5 times 4 minus 32 plus 15. On the right side, we'll get 8 minus 5. So on the left, 20 minus 32 plus 15. Does this equal 3? Well, we have negative 12 plus 15. So we get 3 equals 3. It checks. We have the correct solution. We will not do 13 and 14 at this time. So now just go back through, look over anything that caused you trouble the first time through, and think of any questions that you may have. Jot them down to ask in class on Monday.